Hey everyone, Big Mac here. Welcome to another QualQuest video. So today I'm going to do a problem from our most recent test. First, I actually reordered the questions a little bit just to make it easier. First, we're going to have to find a piecewise constant function whose inverse Fourier transform is this weird function, the sine of nx over x, which you may or may not know as, what is that? The sinc of nx over n? No, sinc of nx times n. So first we're going to figure out what that function could be. Okay, so first thing we're going to assume is that it is some kind of box function, or basically outside of the point A, or minus A, it equals 0, and it's flat on top, so it's like a little plateau or mesa type thing. Alright guys, hopefully you guys can see this blue chalk. I'm actually running out of chalk right now. So hopefully you'll be able to see this blue on the board. Basically, we're defining our inverse Fourier transform as 1 over 2 pi, take our function, multiply it times e to the minus ikx, and take a derivative, or integral with respect to x. So for our box function, it was 0 outside of our a bounds, so our integrand is just from minus a to a. Our function was constant inside the box. And we just do our standard, integrals. We do a little bit of rearranging down here, and we get this evaluation. We have b over sine k times the sine of ka, and where again we want that to mimic the sine of nx over x. In this case, k and x are the same thing, just because of the variables that we choose up here. So quickly, just substituting k as x, we want our two sides to match up. So we let b equal pi as our constant to get rid of this pi up here. And then we let our a equal our n, which can vary as, which can vary. So going back to our box function, we're going to have minus n to n and a height of pi inside. Of course, now the question is, what happens as n changes? So now we come to our first question. We want to take our word function, sine of nx over x, and we want to find the limit of it as n goes to infinity. So, like we mentioned earlier, that this sine function is actually the inverse Fourier transform of our nice little box function. And remember that our bounds were from negative n to n. So now if we want to take n to infinity, we can basically just plug those in here for our bounds. So we're going to have pi e to the minus ikx dx. We can pull out the pi, and then we're left with the integral from e to the minus ikx from negative infinity to infinity. So in the sense of distributions, if you're taking a complete smooth function and then you try and take a transform of it, basically you're going to wind up with this delta function, which, like we mentioned in a previous video, basically is 0 everywhere, but infinite at the point 0 in this case. So that's part A for this question. So now we have our second question. If we take the absolute value of our sine nx over x, and we integrate that from negative infinity to infinity, is this value finite? That's also that's the same way to ask, is this function in L1 space? If we were to try and, make a graph of it, it would look like a bunch of little humps, which, you may or may not, go to infinity. Obviously, they'll decrease, but the question is, how do they decrease fast enough? Intuitively, you would think no, because sine of nx is going to be on the order of 1. So, if you grade 1 over x, that's the natural log, which diverges. So intuitively, we shouldn't expect this to be finite. Fortunately, to help us in our claim, we have this handy tool. If we have a function that is in a continuous spectrum, basically that just means that the function is continuous all over, then we know for a fact that its Fourier transform is in this L1 space, meaning that, if we take the absolute value of it and everything else, it'll be finite. But if you remember our original function f, in this case, remember where our f hat is our sine nx question now. our function f of x is our box, which is not continuous because it has those drastic cutoff points at plus or minus n. So then, therefore, we know for a fact that this actually does diverge. So no, it doesn't go. So it isn't less than infinity. Our last question involves our same function from earlier, but a little different. So now we want to find the limit as n goes to infinity of this function, nx cosine nx over x squared minus sine nx over x squared. It shouldn't take too much convincing that that's actually the derivative of our original sine nx over x term. So again, the question is, what does this mean in the terms of distributions? So using some distributions notation, basically if we have two functions f and g, I'm just using their parentheses form as the integral of them from negative infinity to infinity, kind of like a convolution. Basically, so remember that the second formula was the derivative of our sine nx over x. So I just have it in here as fn prime to represent the derivative. And let's integrate this with some really nice function phi, whatever you want to call it. So it can either be continuously differentiable or in the Schwartz class or whatever. When we take these distributions, one thing happens that's really nice. If we have a derivative on one side and a really nice function on the other side, basically we can switch the derivative, but we carry out a minus sign as well. So the distribution of our fn prime and phi is the same as the minus negative distribution of fn, and the derivative of our phi function, which we said, since phi is a really nice function, we know that it exists everywhere. So recalling that from our earlier notation that fn is actually the pi times the delta function, basically, not with a little hand waviness, I suppose, basically we have phi of x over here, or phi prime of x, but we'd really like to, have this back in terms of our original phi of x. So let's just do the exact opposite of what we did up here. So let's just take the derivative back, basically. So if we integrate this side, we have pi times delta prime of x, which again has no, makes no real sense in traditional mathematics form, but in these notions of distributions, they can be actually quite helpful. So if we lose the minus sign, since we did another derivative switch, so now we have pi delta prime and phi on the right side. So then that means that, like we said earlier, our fn prime, which was what we were looking for, especially as n goes to infinity, will become delta prime times pi. So hopefully, with these last 2 weeks, we can be able to do a couple more problems, go into them a little more in depth, and make sense of everything. So, Big Mac saying, later.